Our work addresses mitigating controlled flight into terrain, a significant cause of aviation accidents. We propose a parallel autonomy system that operates in the background. It continuously maintains a stochastically validated motion plan designed to autonomously execute a safe maneuver when a terrain collision is projected to be happen. The most traditional systems employ a single fixed recovery maneuver, such as the wings level 5G or 6G pull-up. An extension of this concept utilizes hierarchical planning, which can select from a library of predefined maneuvers such as varied turns and G-pulls. A separate category of planners attempts to move beyond fixed libraries by using sampling-based algorithms to generate escape trajectories. Despite their differences, these methods share common limitations. A critical gap is that they often neglect dynamic uncertainties, and while some may incorporate high-fidelity models, many still lack a rigorous uncertainty quantification framework. Our methodology addresses these gaps with an uncertainty-aware terrain avoidance loop that runs continuously in the background. Instead of a simple deterministic check, our system first projects the aircraft's state forward to a look-ahead time. From there, it propagates a library of predefined maneuvers stochastically, accounting for uncertainties. To accomplish this in real time, we use polynomial chaos expansion. This method creates a computationally fast model that captures the complex dynamics. The system then checks for collisions probabilistically using the Wysochansky-Petunin inequality to obtain a rigorous safety guarantee. The system only intervenes and executes the optimal pre-validated maneuver from its queue if the number of safe, non-colliding options drops below a critical threshold. This stochastic approach is critical because the system must account for uncertainties from several key sources, which are categorized into two main phases: the look-ahead placement and the maneuver propagation. These sources include initial condition uncertainty, which covers the localization and navigation uncertainty of the aircraft's current state and the resulting uncertainty of the projected look-ahead state. Disturbances, such as exogenous factors, also affect the trajectory. Command uncertainty is also included, accounting for the uncertain future pilot input during the placement step and any set point or precision uncertainties during the maneuver itself. Furthermore, model parameters represent uncertainties in the aircraft model, such as mass or actuator variations. Finally, DEM, terrain uncertainty, accounts for database resolution and elevation errors in the terrain data, which is essential for the collision check. A critical feature of our system is its flight envelope awareness. A single fixed maneuver like a 5G pull-up is not always feasible and can be dangerous. As the VN diagram illustrates, at low airspeeds, a high G command either can exceed aerodynamic constraints and cause a stall, or cannot be tracked. Our framework prevents this. By definition, we select dynamically feasible maneuvers by validating them before and after propagation. The system actively filters the maneuver library based on the VN diagram's load factor limits for the current airspeed. Here we see our terrain avoidance system in action within the high-fidelity simulation environment. The visualizations show the system propagating multiple potential escape routes simultaneously. Each of these potential trajectories is stochastically propagated, checked for flight envelope feasibility, and probabilistically validated against the terrain. The system then selects the optimal safe path from this set to execute.